All right, good afternoon, guys. So before we get into the content of today's lecture, I'd like to do a few housekeeping things. So first of all, the tests are being returned in the tutorials this week, if you didn't know that already, if you haven't had yours yet. So you do have that to look forward to. The grades are already all on CU Learn, so you can see how you did. I do encourage you to check that the grade on your paper matches the grade on CU Learn. Mistakes do happen. The onus is on you to check to see if a mistake has happened, and if it has, then we'll correct it. Just like with the assignments, if there's any issues with the grade you got on your test, you should take it up with the TA who marked it. For the tests, that will be either Alexi or Sander. You can talk to one of them. They don't hold office hours, so you'll have to do it during the tutorial, but that should be easy because we all wrote our tests in the tutorial we were registered in, so we're going to those anyway. If not, just look at the schedule and drop in to say hello. Worst case scenario, send an email. Another reminder that I'd like to do is for assignment 2, which is due very soon, we would like it if you could indicate what section number you're in so we can return those papers in the tutorials. So just beside your name, write B1, B2, B3, or B5. Those are the 4 tutorial sections. Don't ask me why they're named that way, they just are. And if you could write that there, we'll return those in the tutorial so we don't have a mess at the end of class like we did last time. On the next assignment and on the next test, I'll leave a spot for that for you to indicate so that they get sorted out properly. Any questions about those course mechanics issues? This is all okay? All right, so last class we finished talking about functions. That was everything I wanted to say about functions for the time being. So today we're going to start on the next topic, which is sequences and sums. This is a part of the course that comes up a lot in subsequent courses. So not everything we cover here will be used, every lecture when you do subsequent theory courses like 2804, 3804, 4804. This stuff does come up a lot, so it's one of the things that you really need to take away from this course. So you really should take the time to understand what's going on here carefully. So sequences, that's what we'll start with. A sequence is really just a function in disguise. It's a special kind of function. So a sequence is a function from a subset of the integers, and typically that subset is 0, 1, 2, 3, or sometimes we leave out 0. So typically it's from the non-negative integers or the positive integers, one of the two. But you could define it with any one of those, any subset. We use a sub n to refer to the image of the integer, the nth integer in this thing. All right, we use a sub n to refer to the image Fn. Sorry, I forgot to say what the codomain is. It's to a set S. So really, a sequence is just like any other function, except the domain is usually the positive or non-negative integers, and we have this shorthand notation where we just say a sub n instead of f of n. We call an a term of the sequence. Oops. We call a sub n a term of the sequence. And the sequence itself is, you just surround that in curly braces. So the sequence itself is denoted a sub n, but in a set. It's not quite a set because there can be duplicates, But this is the notation we use, even though it's not completely consistent, I agree. So all of this is a lot of terminology for something that ends up being rather simple. A sequence is what you think it is. So if a sub n is equal to 1 over n, well, the sequence an is just a1, comma, a2, comma, a3, a4, and so on, which we would just write 1, 1/2, 1/3, 1/4, and so on. Right? It's just a bunch of numbers in order. And order means, well, they're coming from this, this subset of the integers, in this case, the positive integers. All right, so that on its own isn't too interesting because we haven't really placed any constraints on what can happen. One nice kind of sequence is called a geometric sequence. So a geometric sequence has a special form. It looks like, well, the first thing is a, the next thing is a times r, the next thing is a times r squared, then a times r cubed, and so on. That's what a geometric sequence looks like. And here, a is just called the initial term, which is some real number. And r is called the common ratio, which is also a real number. Okay. So here are some examples of geometric sequences. If I look at the sequence b sub n, where bn is minus 1 to the n, well, that's a geometric sequence. The initial term, well, you figure out what you get when at the very beginning of the sequence, that's minus 1. And r, the common ratio, is minus 1. Because to get to the next term, you multiply the previous one by minus 1. Now, this is minus 1 assuming that it starts at 1. If you started at 0, then it would be 1. Okay? So what does the thing look like? It looks like minus 1, 1, minus 1, 1, minus 1, 1, and so on. That's an example of a geometric sequence. That's kind of a weird one. Let's do a more normal one. Let's say we have Cn, and Cn looks like 2 times 5 to the n. So it turns out this is also a geometric sequence. What's a here? Any ideas? So remember, a is the initial term. It's the very first term. So that's when n equals 1. Yeah? Yeah, it's going to be 10. When n equals 1, 5 to the n is 5 to the 1, which is 5, and 2 is just 2, so it's 2 times 5, which is 10. What is the common ratio here? What do I do to get from one term to the next? Yeah, I just multiply by 5. So r equals 5. All right. So this sequence looks like, well, it starts at 10, and to get another term, I multiply by 5. So 10 times 5 is 50, 55 times 5 is 250, 250 times 5 is 1250, and so on. Yeah? Yeah, so r is just what you need to do to get to the next term. So if the general term looks like 2 times 5 to the n, the next term will be 2 times 5 to the n plus 1. And that's the same as multiplying the last one by 5, because 5 to the n plus 1 is just 5 times 5 to the n. Other questions? All right, so now that we have this, we can see another slightly more complicated example. Let's say we have the sequence dn, where dn is defined as 6 times 1 over 3 to the n. What's the initial term here? 2, right? If I have n equals 1, then that's 6 times a third, which is 2. And what's r? 1/3, exactly. Right, it's the same pattern as before. So what does this sequence look like? Well, the initial term is 2, and to get to the next thing, I multiply by 1/3. So the next thing is 2/3, then 2/9, then 2/27, and so on. So this is just one type of sequence. Not all sequences look like this. It's just geometric sequences have these nice initial terms and common ratios. That's one type of sequence. Not all sequences fit into this framework. So Bn, Cn, and Dn are all geometric. There's other types. Another one is called an arithmetic sequence. So an arithmetic sequence has the form a, then a plus d, then a plus 2d, then a plus 3d, and so on. Okay. Here, a is still called the initial term. Just like before. D is called the common difference. Right? This is a difference because here we're adding another d each time. You could read this as a plus d, a plus d plus d, a plus d plus d plus d. All right? Every time to get to the next term, you add another d. That's why it's the common difference. If you subtract 2 consecutive terms, your answer is d. Whereas in a geometric sequence, if you divide 2 consecutive terms, your answer is r. Divide goes with ratio, subtract goes with difference. That's why we have these 2 terms. All right, so let's see some examples of these. Let's say we have S sub n, where Sn equals minus 1 plus 4 times n. So what's the initial term here? Okay, so you could say, I mean, there's really 2 different plausible answers. It depends on whether you mean the first term starting at 1 or starting at 0. And that sort of makes sense because when I was defining the term sequence, I said it was either from the non-negative integers or it was from the positive integers. So really I haven't given you enough information. In the last example, we always started it at 1. Let's start this one at 0. So the answer is indeed minus 1. So these ones will say we start at 1. These ones will say we start at 0. It doesn't matter what you do as long as you explain what you've done. So in a question on a test or an assignment, I would tell you what we're starting at. And similarly, if I asked you to give me a sequence, you would have to tell me what you're starting at. I'm going to do examples of both so we get a feel for how to do both. So if we're starting at 0, well then n is 0, so the initial term is minus 1. All right? And what's the common difference here? 4. Right? And I get that from here. If I increase n by 1, I will add 1 more 4. All right. So what does this sequence look like? Well, I start with the initial term, which is minus 1, and then I keep on adding 4 to it. All right, another example. Let's say I have Tn, and it's defined by Tn equals 7 minus 3n. This one's a little bit different from before. What's a going to be, assuming we start at 0? 7. And what's the common difference? Yeah, so here it's going to be negative 3. And the reason is, if you look at the definition of arithmetic sequence, it's a plus here. So really this thing is 7 plus minus 3 times n. That's how you would write it if you wanted to sort of cram it into that definition. So given that, the common difference is in fact minus 3. And you can see this when you start plugging in values to see what you get. The initial term is 7, and then the next one is, well, 7 plus minus 3n means I take 3 away to get 4. And then I would get 1, and then minus 2, and then minus 5, and so on. So it happens that this one gives me negative numbers as I move along in the sequence, but that's okay. The important thing was that I started from non-negative or from positive. In this case, from non-negative. All right. Any questions about sequences? So I don't cover too much about sequences because that's not really the interesting part. The interesting part is what you do with them when you sum them up. So that's why I'm going through this quickly. The other reason I'm going through this quickly is that these things are just functions, and you already know about functions. These are two special types of functions, if you like. One's a geometric sequence, the other's an arithmetic sequence. Right? There's not too much involved there. So one common operation we do with sequences is to compute a sum of certain portions of that sequence. And this is something that has a lot of applications. Doing what I'm about to describe happens all the time in computer science. All right, so suppose we have some sequence. Let's say it looks like A1, A2, A3, goes on for a while. Eventually it's AM, maybe AM plus 1, AM plus 2. Continues for a while, eventually it gets up to AN, and so on. So this is some long, infinite sequence, and these are the terms in some order. We skip a few occasionally, but this is what the thing looks like. What we might want to do is consider the sum of part of this sequence. So we want to consider what happens if we sum from AM to AN. So that means what is AM plus AM plus 1 plus AM plus 2 plus all the way up to AN. That's what I'd like to know. Now maybe M is 1 and N is still N, and in that case we can start summing in the beginning. But in general you can sum from anywhere you like. And we'd like to know what that sum is. We'd like to evaluate it. Of course we can only do that if we know what the sequence is. There's a shorthand for this notation called sigma notation. So this thing here is written the sum from I equals M to N of A sub I. So that's a lot of notation. So let me explain what these things are. n is the upper limit. And that makes sense because it's on top. M is the lower limit. And that makes sense because it's on the bottom. And this variable I is called the index of summation. And you can think of it as kind of a temporary variable that keeps track of the index of the term you're currently looking at. Okay? There's nothing special about using I. I could have used j, but I would have to change j here and here. So you can use whatever letter you like, but you have to be consistent. Well, I mean, it has to be unused. So some people who come from programming backgrounds find it useful to think about sigma notation in terms of for loops. Okay? So if you find this helpful, go with it. If you don't find it helpful, then you don't need to use it. So it is sometimes helpful to think of sigma notation in terms of a program. So if I have the sum from I equals m to n of ai, that's exactly the same as the following program, which I'll write in pseudocode. So it's not really any code. Let's say a initially equals 0, and then for I equals m to n, I do the following. I set a to be equal to a plus, and then the ith term. And then once that's done, I return a. That's how you can think of it if you want to think of it in terms of a program. You don't have to think of it this way, but if you find it helpful, feel free to. All right. Any questions about this notation? Yes?
I into what of summation?
Index of summation. Other questions? All right. So let's see some examples. Hopefully this will make it clear. What is the sum of the first 100 terms of a sub n, where a n is equal to 1 over n? Well, that's just the sum from I equals, we'll say this starts at 1, and this one kind of has to start at 1, because if you started from 0, the first thing isn't defined. So it's the sum from I equals 1 to 100 of a sub I. And that's really the same as I equals 1 to 100 of 1 over n. 1 over I. So someone asks you, what is that sum? You can tell them this, and that is technically correct, but probably not what they meant. Right? They were probably looking for a number. But this is still the answer. It's just a convenient way of expressing the answer. So does everyone see how this is the answer to that sum? It's just a different way of writing that sum. Question? So this includes, so if you look at the definition here, this includes AM and it includes AN. So it includes both the upper limit and the lower limit. Both of those are included in the sum. If you're coming from a Python background, you might find that a little bit surprising. This is how we do it in math. Other questions? All right. So let's see another example. In this one, we will actually work all the way to a number. The sum of the first 5 squares, starting at 1, say. All right, so notice that I'm not explicitly giving you a sequence here, although there is this sequence that's implicit in the question. Right? The sequence is the sequence of squares, and I want to know what the sum of the first 5 things in that sequence is. So this would be the sum from I equals 1 to 5 of I squared. Because I don't want to know the number, I want to know the square. So this is the sum of the first 5 squares. Does everyone see that? Questions about what I've done so far? All right. One thing I'll remind you of here, this is exactly the same thing if I had said j equals 1 to 5 of j squared. That's completely okay. Right, they're exactly the same thing. All right, so if I write this out the long way, this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Right, that's what that expression is. And now I can simplify this. This is 1 plus 4 plus 9 plus 16 plus 25. And if you sum those together, you get 55. So the answer to this sum is 55. Now in this particular case, we didn't really get anything by going to the summation form. Right? We could have done that without taking that detour. And in fact, you don't need it here. I'm just doing this to get you comfortable with the notation. Later on, we'll see that there really are benefits from going to this other notation. We just need a little bit more practice before we get there. All right. So now that I've defined what sums... question first? How I get from here to here? So you don't have to do that. I'm just explaining that they are equal. And the reason they're equal is because the name of the variable you use for the index of summation doesn't matter. You can pick any letter you want. I mean, as long as you're not using it for something else, because then it's confusing. Yeah?
Do both the bounds have to be defined, or can you use the notation to define the sum of an infinite sequence?
You can use it to define the sum of an infinite sequence. We'll see that in a little bit, but that's not really what this course is about. But yes, you can definitely do that. Yeah?
Is that when you find the sum of an infinite sequence, isn't that like the integral?
It's related to the idea of an integral, except in this, if you use a summation, you're summing up discrete things. So terms of a sequence are discrete things, whereas when you use an integral, you're summing up sort of a continuous thing. You may see later in Comp 304, I cover it when I teach it, these ideas aren't actually that different, and you can use one to approximate the other. Other questions? All right. So now that we've defined what these sums are, what this summation or sigma notation is, the next natural question is, okay, well, what can you do with it? Why would I ever want to do this? So what I'm going to describe now is things you can do to sigma notation to change it around to suit whatever your need is. So one thing you might want to do is change lower and upper limits without affecting what the sum is. So I'd like to change the values of the lower and the upper limits without changing what the sum evaluates to. Okay? So as an example, if I had the sum from, I don't know, I equals 1 to 5 of I squared, right, the sum I had before, let's say that I would like to write that sum not with lower limit 1 and upper limit 5, but I'd like to write it with lower limit 0 and upper limit 4. But I'd like the sum to be the same. So how do we write this with lower limit 0 and upper limit 4? So one thing you can't do is just change it to be I equals 0 to 4 of I squared, because then the sum is 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared, and that's definitely not the same thing as 55. Right? So you can't just change those and hope for the best, because we want the sum to work out exactly the same. One thing before we decide how to do this that gives us hope that it's possible is we say to ourselves, okay, well, when the sum ran from 1 to 5, how many terms were there in the sum? 1, 2, 3, 4, 5. So there's 5 terms. If I started at 0 and take it to 4, then there will be 0, 1, 2, 3, 4. So in both cases, there's 5 terms. And that kind of fills me with hope a little bit, because that means that I have the same number of terms in the sum. I just need to change what they are. We'll talk more about counting how many terms there are in a bit. So that being said, I would like to write this such that I get I equals 0 to 4 of something. What's the something that I need? Yep.
I plus 1 in brackets all squared.
I plus 1 in brackets all squared. All right, so if I do that, let's think about what happens. This thing here will be 0 plus 1 squared, plus 1 plus 1 squared, plus 2 plus 1 squared, plus 3 plus 1 squared, plus 4 plus 1 squared. And then we stop, because 4 is the upper limit, and 0 is the lower limit. And if we simplify this a little bit, this is just 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And if we look up here, it's exactly the same as beforehand. So this is exactly equal to the sum from I equals 1 to 5 of I squared. Okay, so this tells us that, we did it. This sum is exactly the same in the sense that it evaluates to the same number, except its lower limit and upper limit have been changed. Now, it's not obvious why we would want to do this yet, but I will tell you that it comes in very handy later. And the reason it comes in handy is because sometimes for certain types of sums, we'll have nice formulas that let us evaluate them exactly. But those formulas only apply to certain upper and lower limits. So if we don't have those upper and lower limits, we might want to change them into something that we do have a formula for. And we'll see that later. Is everyone okay with this example? So for this, what you have to do is think about what this term would have to be to mimic this other term. That's all you have to do for these. We'll see lots of examples. Another operation you can do is splitting a sum up. So let's say we had a sum from I equals 1 to n of a sub I. That's exactly the same as the sum from I equals 1 to 5 of a sub I, plus the sum from 6 to n of a sub I. Right? That's exactly the same thing. One thing you do need to be careful of is that the upper limit of the first sum should be 1 less than the upper limit of the next sum. If you made them both 5, then you would be counting one of the terms twice, and you don't want to do that. It won't be equal. So one thing that's handy is that you can split sums up. And this is useful if maybe you don't have a formula for this thing here, but you do have a formula for both of these things. All right. Now let's say that you didn't have it quite in this form. Let's say you had a sum that started from 6 and went to n. You could split that up by rearranging this. So by rearranging, we get the sum from I equals, say, 6 to n of ai is equal to the sum from I equals 1 to n of ai minus the sum from I equals 1 to 5 of ai. Right? All I did was rearrange the previous equation. So this says if you have a summation that ignores maybe the first couple of terms of some other summation, what you do is you take the original summation and you subtract off the things you're not interested in. Right? If I wanted to know the sum of all the numbers from, say, 5 to 100, I could sum up the numbers from 1 to 100 and subtract off 1 plus 2 plus 3 plus 4. Right? That would do the job. Again, it's not clear why I would want to do that, but maybe I have a formula for when the summation starts at 1. So notice both of the summations here, the lower bound is, or the lower limit is 1, and here the lower limit is 6. If I have a formula for the case when the lower limit is 1, then I would definitely want to split it up this way, because if I have a formula for this and I have a formula for this, well, then I have a formula for the whole thing. We haven't seen any of these formulas yet. I'll get to them. But this is why we want to do this operation. Another thing that you'll encounter is nested summations. So summations can be nested. So what this means is I could have the sum from I equals 1 to n of the sum from j equals 1 to n of, I don't know, let's say I times j. So you're really bracketing like this. You evaluate this first sum, and then you plug that answer into the second sum and evaluate that. One important thing you have to notice here is that my indices of summation are different. Right? It wouldn't make sense if they were the same, because then I wouldn't know which one it went with. Right? I wouldn't know if I meant the I in the inner sum or the outer sum. So this sum here is the inner sum, this sum here is the outer sum. If it's helpful for you, you could think of this as a program. So this thing here is exactly the same as a equals 0 for I equals 1 to n, for j equals 1 to n, a equals a plus I times j, and then at the end I return a. If that's helpful for you, then you can think of it that way. Notice that this summation we call nested, and if you're familiar with programming, these for loops are nested. That's where we get this terminology. So let's do an example, because this is starting to get a little bit complicated. The sum from I equals 1 to 4 of the sum of j from j equals 1 to 3 of I times j. All right, so what you're doing with nested sums is you always work from the inside out. That's what you always, always, always do. That's really important. If you encounter one of these, work from the inside out. So we leave the outside alone for now. And now we think, what does the inside sum evaluate to? Well, the inside sum goes from j equals 1 to 3. What's the first term of the inside sum? So completely ignore the fact that we have this outside sum for the time being. Pretend we just have the inside sum. Yep? Yeah, it's going to be I. 1 times I, if you like. Because when j equals 1, what we get here is I times j. j is 1, so we get 1 times I. What's the second term going to be? 2 times I. What's the third term going to be? 3 times I. And there's only 3 terms, so we stop there. Notice what I've done is I've got rid of one of the sums. Right? That's useful because the fewer sums we have, the closer we are to an actual number. One thing I'll point out here is you should always think about the kind of answer you got out of your sum. So if I have a sum that goes from j equals whatever to whatever, where the index of summation is j, the answer I get will never have a j in it. Right? If I'm solving a summation whose index of summation is j, j won't be in my answer. It can't be. It was only a temporary variable that held these values as it went through the sequence. So in this case, I'm summing over j, and j doesn't appear anywhere in my answer. So I'm happy. Right? I'm summing over I, but that's in the outside summation. It's okay if my answer is in terms of I right now. I'll get rid of that later. So when you've solved a sum, your answer should not be in terms of that index of summation. If it is, you've done something wrong. All right. So now what we do is we clean this sum up a bit. This is the sum from I equals 1 to 4 of, well, we have 1i plus 2i plus 3i, so that's just 6i. So now we do the same thing. What's the first term of this sum going to be? So I equals 1, and we multiply by 6. So the first term is going to be 6. What's the next term? 6 times 2 is 12. The third term? 18. And the fourth term? 24. And if you add all these together, you get 60. So this is what that sum evaluates to. This thing right here is exactly equal to 60. Notice that when we evaluated this sum here, the outer sum, the index of summation of that sum was I, and our answer doesn't have an I in it. Right? It shouldn't, because if it does, I've done something wrong. Your answer to these can't have any index of summation in it. It could be in terms of the upper or lower limit. That does happen, and we'll see examples. But what it definitely can't have is the index of summation in the answer. All right. So there's one operation that we kind of did here but didn't really talk about, and that's working with this sum right here. We had this 6 times I thing. So let's think about that for a second. The sum from I equals 1 to, I don't know, let's say n of 6i. Well, that's the same thing as 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4, and so on. And if every term is multiplied by 6, then I can factor that 6 out. So that's 6 times 1 plus 2 plus 3 plus 4, and so on. So really, another way to write this is 6 times the summation from I equals 1 to n of I. So what you can do is you can factor things out. In this example, there's nothing special about 6. It works for any number. And there's nothing special about I. It works for any function. What you have to be careful about here is we can only factor out 6 because it's a constant. And by constant, I mean it doesn't depend on the index of summation. Right? If that were an I, so let's say this was I squared instead of 6i, well, I couldn't factor out the I. And that makes sense if you think about it, because, well, then my answer would be in terms of I, but I is the index of summation, and I can't have that. It doesn't make any sense. So that's how you factor things. You can factor out a constant inside the sum by bringing it outside of the sum. Any questions so far? All right. So here's another example of factoring that's a little bit more complex. Let's say we have the sum from I equals 1 to 4 of the sum of j equals 1 to 3 of I times j. Right, this is in fact exactly the example we saw before. I'm going to solve it a little bit differently in a way that maybe you find easier. So notice that this thing here can be bracketed like this. And I said we always work from the inner summation out. So this inner summation is the j equals 1 to 3 of ij. Is there a constant there? Yep. Right. In the inner summation, I is a constant. Right? Because the only thing that's not a constant in the inner summation is j. So in fact here I am allowed to factor out I. I can only factor it out of the first sum, so I have to put it there. And then the rest I have is j equals 1 to 3. What's left is just j. So I factored out that I, and I can do that because the index of summation is j. I can't factor the I out here because the index of summation is I. It's not a constant. So whenever you want to factor something out, you ask yourself, is it the index of summation? If it is, then you're not allowed to factor it out. If it's not, then you are allowed to factor it out. So this simplifies matters a little bit. Because now I say to myself, okay, well, now I have this simpler sum. This is just the sum from j equals 1 to 3 of j. What's that sum? Right, it's just 6. So now I have 6 times I. And now I can do the same trick. I have a 6 here. 6 is not I, right? 6 is a constant, right? It's really obvious it's a constant there because it's an actual number. So I can factor the 6 out to get the sum from I equals 1 to 4 of I. What's the sum from I equals 1 to 4 of I? 1 plus 2 plus 3 plus 4 is 10. So this is 6 times 10, and that's 60. And not too surprisingly, if we look up here at our previous answer, we got 60. So it matches up. And once you get more experience, you'll find that this approach is easier because it has fewer steps. And the more steps you do, the easier it is to make a mistake. Any questions about factoring? Yeah?
Actually, do you have some examples for splitting sums?
Yes. In fact, I will do that right now. So splitting, is another technique that you can use to make sums simpler. So you can split over addition. So you factor over multiplication, you split over addition. So let's say we had something that looked like this. Let's say it's the sum of I plus 2 to the I. That's exactly the same as the sum from I equals 1 to n of I plus the sum from I equals 1 to n of 2 to the I. This is how you split terms of summations. You can also split the summation into separate sequences, if you like. But this is the more common operation that we'll see. So if you have a sum that consists of terms that are added, then you can split that summation up so that it just adds each term individually. And this is a very useful operation because most of the formulas we have are for kind of simple sums. So we don't have a formula for 1 plus 2 to the I, but as you'll see, we do have a formula for I, and we do have a formula for 2 to the I. So that's how you solve these things. That's why you would split up this summation. One thing I'll stress is that this does not work for multiplication. You cannot do that. So if I had something like, so I'll say, this does not work for multiplication. So the sum from I equals 1 to n, let's say it's I times 2 to the I. So instead of plus, it's times. It's not the same as the sum from I equals 1 to n of I times the sum from I equals 1 to n of 2 to the I. Unfortunately, that's not how it works. If you don't believe that, try it. Try a few of these and you'll see very quickly that it's not always true. Right? Sometimes you can make it work, but in general it does not work. Okay. Any questions? All right, so what have we done? We've learned how to split sums two ways. One is split a sum into two sums based on which terms they cover. Another is to split a sum in terms of taking one term of that sum and splitting it into two parts rather than the sum into two parts. We've learned how to factor things out, and we've learned how to reindex sums, so change the upper and lower limits. All right, so let's think a little bit about maybe some kinds of formulas that we can use. So I've been alluding to the fact that there are formulas for some of these sums, so let's go over some of them. One useful one is the sum of a geometric sequence. So this is why I told you about geometric sequences, so I could tell you this. This is a really useful formula, and it comes up a lot, and I strongly suggest you memorize it. All right, so let's say we have initial term, initial term A and common ratio R, and they're both real numbers. And let's further assume that R is not 0, right? Because if R is 0, that's pretty boring, right? The common ratio is 0, so everything's 0. What if we want to know the sum from I equals 0 to n of A times R to the I? Right, that's the general term of a geometric sequence. And I'm starting at 0 here, to be clear. We have a formula for this, and the answer to what this sum is depends on what R is. So there's two cases that we'll consider. One is when R is equal to 1, and one when R is not equal to 1. So if R equals 1, that means every term is the same. Right? If the common ratio is 1, then to get from one term to the next term, I just multiply it by 1. So that's the same as doing nothing. So every single term has to be whatever the initial term was, which is A. So I have A, and then I multiply that by the number of terms that I'm interested in. How many terms am I summing up? N or n plus 1. So this is what it comes down to. If this were the sum from I equals 1 to n, how many terms would there be in that sum? N, for sure, right? If it was a sum from 1 to 5, it would be 1, 2, 3, 4, 5. 5 terms. Therefore, if I start the sum at 0, I must have one extra term. And I am starting it at 0 here, so that must mean it's A times n plus 1. That's the case if R equals 1. The other case is if R is different from 1. And this one's a little bit less obvious to see. I'll tell you what it is, and then I'll show you why. So the sum is A times R to the n plus 1 minus A all over R minus 1. And this is for the case if R does not equal 1. One thing you might notice about this is that it's pretty important that R is not 1. Why is it important that R is not 1? Yeah, you divide by 0, right? Because if R is 1, the denominator would be 1 minus 1, which is 0. So this is the formula for the sum of a geometric sequence, and it depends on whether the common ratio is 1 or not. All right. It's not at all obvious, based on what we've done so far, why that would be the answer. It's hopefully clear why the top one is the answer, but it's not clear why the bottom one should be the answer, so I'm going to prove it to you. All right, so let's say, just for shorthand, let's let S equal the sum from I equals 0 to n of AR to the I. Right, just so I don't have to write it each time. All right, so what I'm going to do is I'm going to look at the value R times S. All right, I'm going to take S and multiply it by R. All right, so I have R times the sum from I equals 0 to n of AR to the I. Right? That's just the definition of S. Okay, well, if I can factor the R out, then I can certainly distribute it back in. So I'm going to do the opposite of factoring here. This is exactly the same as the sum from I equals 0 to n of R times A times R to the I. And if I remember my rules for powers, this is exactly the same as the sum from I equals 0 to n of R times A, I'll just say A times R to the I plus 1, right? R times R to the I is just R to the I plus 1. Is that okay? So far so good? Okay. What I'll do now is I will re-index this summation. I want this summation to start at 1. So this is the sum from I equals 1. And if it starts at 1, what should it stop at? N plus 1, right? I'm adding 1 to the lower limit, so I should add 1 to the upper limit as well. And now what goes inside? Well, to answer this, think to yourself, what did this sum go through before? So at the very first term was I equals 0, and this exponent was 1. Yep?
What are we raising to the I plus 1? R or A times R?
It's just R.
Okay.
Yeah. Yep. I subtract what, sorry? So I'd have AR to the what? I plus 1. Minus A? Oh, minus A down here? Not quite. So think about what this went through beforehand. So the AR is going to be the same. The only thing that's going to be different is the stuff around the index summation. So when I was 0, the very first term, I had exponent 1. When I was 1, the very next term, I had exponent 2. So what I had was AR to the 1, AR to the 2, AR to the 3, AR to the 4, and so on. The very last term here was when I equals n, and in that case I had AR to the n. N plus 1, sorry. So really, it's just AR to the I. Right? The very first term above had exponent 0 plus 1, which is 1. And my very first term has exponent 1. The very last term up here had exponent n plus 1. And my upper limit here is n plus 1. And it increases 1 each time. And I have the same number of terms. So these two sums must be exactly equal. Does everyone believe that? This is exactly the same operation as I did when I was changing the bounds the first time, except this is a little bit more complicated because it's in an exponent. Does that make sense? Okay. So now that I've done that, I'm going to say, this is good, but I'm trying to figure out something about the sum from 0 to n. So I'd like to kind of go back to that. And the way I kind of go back to that is I split this sum up and I say this sum is exactly the same as the sum from I equals 0 to n of AR to the I plus the very last term. plus the last term minus the first term. Right? I'm taking this sum to go from 0 to n. Here, there was no 0th term. So when I equals 0, I get AR to the 0, which is what? A. So I didn't have this up here, but I do have it down here. So to make it equal, I have to subtract an A. Right? Because down here, I have this 0 term, but up here I didn't have this 0 term. The other difference is now the upper limit is n, but before the upper limit was n plus 1. So I've missed one of my terms. So I have to add that back in. The term I've missed was when I equals n plus 1, so the term is AR to the n plus 1. Okay? Does that make sense? I just think about the terms that are missing or have been added from the previous summation. All right, and now I do something I think is pretty neat. This thing here is the sum from I equals 0 to n of AR to the I, and I already have something called that. It's S. So this thing here is just S, and I'll write this a slightly different way. I'll say plus AR to the n plus 1 minus A. All I'm doing is subbing in S for something that it's equal to. So what this shows is the following. It shows that R times S is equal to S plus AR to the n plus 1 minus A. So let's write that down. R times S is equal to S plus AR to the n plus 1 minus A. So what we're trying to do is find a formula for S. So what we should do is solve this equation for S. So if I wanted to solve this for S, what would I do? What is S? Does anyone see? So I can do this in steps if you don't see it. So RS equals S plus AR to the n plus 1 minus A. Therefore, RS minus S equals AR to the n plus 1 minus A. And now I factor out this S on the left side to get S times R minus 1 equals AR to the n plus 1 minus A. And now I divide through by R minus 1. So S equals AR to the n plus 1 minus A over R minus 1. And notice I'm allowed to divide by R minus 1 because I know that R is not equal to 1. If R were equal to 1, that wouldn't be valid. And notice that this S is exactly what I was trying to find. Right? This S here is the sum from J, well, I'll say I equals 0 to n of AR to the I. So I have this formula right here for it. And if I look back up at what I said it would be, it's exactly that. So this is an example of how you solve one of these summations. Does that make sense? This derivation is tricky because you probably haven't seen anything like this before. This is the kind of things that we do with sums. Turns out that there's a lot of other useful formulas. And I'll go over some of them now. One is that the sum from I equals 1 to n of I, so 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, that's exactly equal to n times n plus 1 over 2. And I'll do an example that proves that in a second. For now, I'll just give you the formulas. That's one really useful one, comes up all the time. Another one is the sum from I equals 1 to n of I squared, so the sum of the first n squares, that's equal to n times n plus 1 times 2n plus 1 over 6. That's a handy one, and we'll learn how to prove this too. The sum from I equals 1 to n of I cubed is equal to n squared times n plus 1 squared over 4. And you might notice that there's a relation between that and the first one. We also have a few infinite ones, which was asked about earlier. The sum from I equals 0 to infinity of x to the k, or sorry, x to the I, is equal to 1 over 1 minus x as long as the absolute value of x is less than 1. If it's not, then that sum is not anything in particular. And another interesting one that's an infinite sum is the sum from I equals 0 to infinity, or sorry, I equals 1 to infinity of, I don't know why I keep writing k, I x to the I minus 1 is equal to 1 over 1 minus x squared. And again, that's only when the absolute value of x is less than 1. Does anyone see why the last one is true, given that the second from last one is true? It's not completely obvious, and you don't need to know it to be in this course. What happens if you take the derivative of this with respect to x? You get ix to the I minus 1, which is exactly what you get here. That's not a coincidence. All right, so let's try to derive one of these ourselves. The last two are more complicated than we need for this course. I would definitely suggest that you memorize the geometric series one and at least the first two here. You'll need those. If you don't want to memorize them, learn how to derive them on your own. All right, so let's derive the first one. So that's that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. There's actually a backstory to this one. It's probably not entirely true, but I'll tell you what the story is. So many years ago, there was a famous mathematician named Gauss. And at the time, he was just a schoolboy, and him and the rest of his class were acting up. The teacher was getting annoyed by this. So to quiet the class down, the teacher did what any good teacher does, and that is give them busy work. So the busy work was the following. Sum up the numbers from 1 to 100. And these are just elementary school children, so they know how to do those additions, but it would take them a while, right? It would take most people a while to do that. And summing the numbers from 1 to 100 is essentially exactly what this thing is doing. And Gauss came up with a neat trick that let him do this very quickly. So I'll show you what the trick is. So just like last time, I'm going to use s to denote the sum I'm interested in. The sum from I equals 1 to n of I. And what Gauss supposedly did was he wrote down this sum in two different ways. The first way is 1 plus 2 plus 3 plus 4 and so on, all the way up to n minus 1 plus n. Right? That's what the sum is if you wrote it out the long way. That's not the only way to write this sum down, though. You could also write it down in reverse. You could say it's n plus n minus 1 plus n minus 2 plus n minus 3 all the way down to plus 2 plus 1. Right? Both of those are perfectly valid ways of writing down this sum. The ingenious part came from taking these two equations and adding them together, which is valid. You can add two equations together. So if we add s and s, we get 2s. And now we add each one of these terms. N plus 1 is just n plus 1. 2 plus n minus 1 is what? N plus 1. 3 plus n minus 2 is also n plus 1. 4 plus n minus 3 is also n plus 1. This pattern continues. N minus 1 plus 2 is also n plus 1. And n plus 1 is, of course, n plus 1. How many terms are there in this sum? N. So the sum itself is n times n plus 1. But that's not the sum we're interested in. That's twice the sum we're interested in. And therefore, S is equal to n times n plus 1 over 2. That's one way you can derive that. Any questions about these? Yeah? The boxes trick? I'm not sure what you mean. Yeah, we can talk after. Other questions? All right, so that's actually everything I want to say about functions. Later on in the class, we'll prove more of these are true, but we actually don't have the proof technique we need to do the rest of the proof, so we'll defer that until later. Next class, we're going to start talking about algorithms, but that's it for tonight.